For our thermodynamics project, we decided to go back to our childhood of burning ants with the magnifying glass and try to burn popcorn kernels or make them pop into popcorn with the magnifying glass. We chose the day before this one. As you can see right now, it's pretty sunny, but there's still a little bit of cloud coverage. It was pretty much the same yesterday, although the weather leading up to this point was pretty cloudy with a lot of rain, so as a backup, we had a very high wattage heat lamp. All the tools that we used were pretty straightforward. You can get them at any hardware store, and the prime ingredient, of course, you can get at any grocery store. For the magnifying glass experiment, it's really very simple. We have a popcorn kernel over here on the concrete. We don't want to be setting anything on fire accidentally. And we have our magnifying glass. Now, there's a couple key things to remember with the magnifying glass. You want to hold it up to the sunlight so that way the face is almost perfectly normal to the sun's rays, and you can tell when it's facing the ground. You can see that focal point of almost a perfect circle inside of it. And then you move it closer and farther away from the ground, and that area gets bigger or smaller. Now, to get the best heat, concentrated heat, you want that area to be as small as possible. And then once you find that, you hold it over your popcorn kernel, and then you wait to see what happens. When we first started the experiment with the heat lamp, we wanted to see if the base temperature of the concrete had an effect of whether or not the popcorn kernels would pop, and if they did, how long. So, the base temperature of the concrete was about the same temperature as the air. It was about 70 degrees at the time. So after the heat lamp had been on for several minutes and the concrete itself had heated up to over 300 degrees, we threw some more popcorn kernels on there to get a more uniform heat transfer. And sure enough, that did have a very big effect. As you can see, the kernel is on fire. It's been cooking like this for about 5 minutes now. And it's smoking. You can see, if I was getting close enough, you can see the discolorations and you can see the smoke. Earlier I was getting temperature readings between over 150 degrees. I thought I saw a spike of 180.
Where's the ant? I'm going to find the ant.
There we go. It is at 200 degrees. 200 degrees. That is crazy. And it's not popping, it's just burning.
I'd say that's due to the underside not being as hot as the top.
Probably. It's not good.
Yep,
I think it's just not an even coating. This is a spot cooking.
A direct UV or infrared heat, so if the bottom of it is not going to be near as hot as the top.
Yeah, the concrete near the kernel is still only at about 100 degrees. Then we go back to the heat lamp, and we don't see any noticeable changes, or at least not visual. The area under the kernel is about 200 degrees, and from the best reading I can get of the kernel itself, it's at 260. Still not popping. These are hilarious results.
But that way...
Well, this is the result of the first kernel, and we're moving on to another one, but that sucker is cooked, but it has not popped. Kernel number 2 has been cooking for about 45 seconds, or closer to a minute, not 100% sure. Concrete around it's at 100 degrees, and the kernel itself, from the best reading I can get, it's about 110, 115. There we go.
You should go pop a bag of popcorn.
Still nothing. I imagine the difference in the fact that these kernels are catching on fire and how those are only getting warm but they're not popping could just due to the heat transfer area. I mean, under the heat lamp, we've got a much wider area that the heat's going down towards. It's cooking the entire concrete. Versus this one, we've got a tiny area, not even a square centimeter.
Very high intensity directly from the sun. Double convex lens is causing the image of the sun to be put onto the kernel.
It's not burning yet, but I suspect it will.
Maybe you should heat the ground up first until it's hot, and then put the kernel on there.
Concrete's still around 100 degrees. Kernel is up to 120 if I saw that right. There we go, 135. The heat lamp has been on for almost 40 minutes and still no popping, but we are getting crazy, crazy temperatures. The concrete under the kernels is just under 400. The kernels themselves, if I can aim, the wind is probably not helping, but they were about 400 degrees earlier. Now I'm getting about 360, 370. Oh, there we go, 395. To do the calculations for all of the experiments, we chose to do the heat transfer by radiation because that was the primary source of heat transfer. And for all three experiments, I used the same information on the popcorn kernels. I've approximated them to be a sphere and found the average diameter and surface area. And after finding all of the information based on the kernel itself using websites, research papers, and our textbook, I went ahead with all the calculations for all the experiments. Before doing the calculations for the microwave data, I did two smaller experiments. I took a regular bag of popcorn and heated it up until almost all of the kernels popped, and then I took the temperature readings of the freshly opened bag and of course the initial temperature before I heated it up. And the second experiment was, again, taking the initial temperatures of just plain kernels, 20 of them to be exact, throwing them into a bowl, a glass bowl, and then microwaving that until they all popped. This was mainly to see if the bag itself had some influence, and I learned later that the bag does have a lot of influence. After calculating all of the data for the microwave based on just the bowl of 20 kernels and the whole bag for both the heat transfer rate and the total heat transfer, I found that the bag had a far better performance of heat transfer, both in the rate and the total heat transfer. The bowl of just the 20 kernels had a total energy transfer of about 65 joules and the rate of about 1 watt, but the bag itself had 75 watts of heat transfer rate and transferred over 10,000 joules of energy. And the reason behind that, as I learned, is that the popcorn bags actually, the reason you have to put them face up is because there is a thin layer of foil on one side of the bag and it provides extra conduction as well as the radiation from the microwave. So that is why the bag will start popping your kernels almost immediately and they reach much higher temperatures. As you can see in the spreadsheet, the bag reached much higher temperatures than the bowl did, based on what I could read. Looking at the data for the magnifying glass, it did have a much better heat transfer than just the bowl of popcorn. However, the rate was surprisingly small. And this makes sense because the area that the heat was being transferred to for one kernel was extremely small. And also, the temperature difference wasn't quite as high as it could have been. The popcorn kernels in the microwave, the highest temperature that I read off of them were in the bag and was over 150 degrees Celsius. This only made 93 degrees Celsius. But the magnifying glass did provide a very high heat transfer and the kernel didn't pop, but it did burst into flame. So there was a very large amount of heat transfer going on there. But the reason we are pretty sure it did not pop, but instead it burned, is because the heat transfer was not uniform around the entire kernel. One side of the kernel was always against the concrete, which did warm up significantly, but it never reached the same temperature as the top of the kernel, which was getting the direct sunlight. So that's why half of it just singed rather than the entire popcorn kernel getting heated to the point where it finally burst. Before I go into detail about what the final data calculations are for the heat lamp, the kernel that did burst under the heat lamp was a kernel that we threw on later. The heat lamp had been running for over 45 minutes, but about 20 minutes in, we threw some more kernels under the heat lamp just to see whether or not the preheated surface area of the concrete would have an effect on the popcorn kernel, and it most certainly did. Because after the one kernel did burst, the two kernels that were still under the heat lamp the whole time, the whole 45 minutes, those never burst. You can even see that in the video. They're significantly darker in color, but they never burst. And the reason for that is because the kernel that did burst had a much more uniform temperature. We think that if we left the heat lamp running longer, the other kernels that had been under there for a long time would have burst as well. Now looking at the data, the heat transfer, or Q, of the kernel was 5 times higher than that of the magnifying glass. That's honestly really surprising. But it also makes the most sense because it reached the highest temperature of anything that we recorded. However, it still was not even close to the heat transfer that was put out by the microwave. Looking back at the data from all 3 experiments, the most effective heat transfer method is still popping popcorn with a microwave in its designed bag, just due to the fact that it had the highest amount of heat transfer out of all of the experiments that we conducted, and it still took a very short amount of time to pop all of the popcorn.